Okay, so good day to all. So this time we are going to discuss the topic economic sections. So actually this is still under beam stresses. So for our learning objectives, at the end of this chapter, we intend to, number one, apply efficiently the Flexure formula in solving problems involving it. By the way, these are objectives under the topic beam stresses, wherein your economic sections will cover number 2, number 3, and number 4, in which we are going to determine the most economical sections of a cross-section through solving the section modulus of a beam, and also to look on the established tables on the geometrical properties of our available geometrical sections. And then we intend to resolve problems first involving shearing stress in the beams, and then familiarize with the units of the shearing stress and the flexural stress formulas. And we also derive the formulas of shearing stress of common beam cross section. So what are the implications of the flexure formula? So of course, from your flexure formula, it was observed that from the neutral axis, as we go outward from that up to the extreme fiber, your stress will, or the resistance, flexural stress resistance is increasing. So as y goes outward from the neutral axis, flexural stress resistance is moving towards its maximum, hence it increases. So the general formula using this y distance referred from the neutral axis is sigma b is equal to my all over I, and the farthest distance is actually denoted by c, so that your stress will be at maximum. So as a criteria, we need to have section modulus, since it involves dimensions in terms of I and the distance from the neutral axis. So section modulus normally is denoted by Z or S. So if it is Z, we are going to use C here, and Z is actually the plastic section modulus, and the elastic section modulus is a general formula wherein we have I all over Y. So Y is the distance from the neutral axis at any layer of your cross section. And again, as we go on the extreme fiber from the neutral axis, that will be our stress at maximum, or flexural stress maximum. That is equal to M over Z. So this is just substituting the value of Z, wherein Z is equal to I all over C. So probably one of the questions, premature question, does it have to be always a rectangular section? So of course, there are a lot of things to consider, like if we intend to use this one, especially if you have a steel section, this may involve a lot of volume, and as you know that the volume is directly proportional to the weight. especially so that the steel section or shapes will have a larger unit weight. And of course, it will affect really your design. So the effect is it would enlarge your design. Okay, it may require large dimensions because of the heavy weight of your self uh, structural element. Okay, so the section is voluminous and it would have a greater weight. So from the formula MC over I, actually we are not just relying on how thick is your cross section. What is important, if your structural elements being used as a flexural member, we need to concentrate the thickness on your flange section. So of course, if you have a rectangle, there is no flange here, or your flange is the width itself, and at the same time, it is a web on it. So remember that a flange is the concentration of your buckling effect. Okay, so if we have an I-beam, so this is the flanges of your member, and the flange is responsible to carry flexural loadings. So your web has a little contribution. This is the web, okay? But the focus of your loading in terms of buckling is actually your flanges. So in the case of rectangular one, you might want to rearrange your shape so that you could save a lot of weight. Just concentrate on the section of the flanges. So that's the rationale in selecting the right section. So perhaps we can consider other sections like a T-bar, hollow steel structure, angle bar, wide flange, I-beam, or channels. So but we must have to, of course, bear in mind that your capacity should always be greater than the required. Okay, the capacity of your member should always be greater than the applied loading. So that is why your section modulus, by the way, this is S required. It is denoted by S because it is elastic in nature, or it could be also Z, or plastic elastic section modulus. So as we can see, S required is greater than or equal to S of live load. So initially, we are going to have live load as a criteria because initially we do not have yet an estimate of your self weight. So the purpose of this criteria is to select from the table the most lightest section so that we are going to check that adding it to S live load, and your S required should be always greater than the actual section modulus of your live load plus your dead load. So dead load is added only after deriving S live load and then selecting an appropriate section to resist your live load. And where shall we get the values? Of course, these are already tabulated in a series of tables on various geometrical shapes. So S required is also should be greater than or equal to, of course, this is just using the formula. Okay, so if we're going to cross multiply this one, will yield to the same formula that we have been using, that the stress, flexural stress is equal to mc all over I, and further it will be simplified to m over s or m over z. Okay, so if we are going to cross multiply this, it will just interchange, so that we can have this expression s is equal to m all over sigma, or this is actually flexural stress, or FB. In some books, this is denoted by FB. Okay, stress bending. So this is maximum since we are dealing with the plastic section modulus. So what I have introduced to you is a while ago that S is elastic, but most of the books are expressing your plastic section modulus in terms of S. So we'll just have to adapt to it. Okay. So as for the resisting moment, we should have placed here M resisting. Okay. So M resisting should be always greater than or equal to the sum of the moment caused by the live load and the moment caused by your self weight or the dead load. And then S resisting is further should be greater than equal to S by the live load or the section modulus required by the live load and the section modulus required by your self weight or your dead load. So moving on, let us consider here an example. So this is called from the book of Hibeler, example 01. So a 10-meter beam simply supported at the ends carries a uniformly distributed load of 16 kilonewton per meter all over its entire length. What is the lightest W-shaped beam that will not exceed a flexural stress of 120 megapascal? What is the actual maximum stress in the beam selected? So as a criteria here, we have given allowable. So remember that this will be your limit or the ceiling for the flexural stress. So it couldn't be that the effect or the moment of caused by the loading should exceed this flexural stress using a certain uh, geometrical shape. Okay. So sigma allowable is given 120 megapascal. And then by and by we're going to check the actual maximum stress in the beam selected. So the first thing to do is to determine the maximum moment of this beam if it would carry the 16 kilonewton per meter uniform load as a live load. Okay. So actually, if we have a simply supported beam, we do not have to do this shear and moment diagram because we have a popular formula in the maximum moment. So if we have a simply supported beam, just bear in mind that the maximum moment is equal to W L squared all over 8. Okay, so in this case, we have 16 times 10 squared all over 8. And this is the maximum. So From that, we can get here the value of 200. Okay, 200 kilonewton meter. And then, based from that, the criteria of your allowable, this is 120. Okay? 120 is the allowable bending stress in megapascal, and that way we shouldn't exceed this one. So we'll just substitute in your formula. So this formula came from this. The flexural stress is equal to M all over S. So further, S is just equal to moment all over your bending stress. Okay. So in this criteria, we're going to determine the required section modulus based from the live load derived, and that is 200 kilonewton meter, and multiplying that by 1 million, of course, to express this in terms of Newton millimeter, so that it may jive with the unit of megapascal here. So from that, we can determine the value of your section modulus in terms of millimeter cube. So we have 1,666,000, or this is 1,666.67 times 10 raised to 3 cubic millimeter. So why do we need to get this one? So that from the table, we can select a value that is greater than this one. Okay. So this is the value. We look at the table for W shapes, or the wide flange table. So this is actually present on some references of AISC. So as we can see in the table, we can select a value greater than this. You might ask that these are, why not this? Because this is less than this one. Okay, and in fact 1770 is next to your requirement. And why do I have to choose this one? Okay, so of course, first thing to do is to look at those sections that is greater than this one. Okay, so first you might want to select this one because this is slightly greater than that. Okay, as well as this section and this section. So actually this three could be your section, but the most economic section out of these three is this one. Okay, why? Remember that this table denotes the depth, okay, and this denotes the weight, and this weight is actually kilograms per meter. So meaning, if the second notation here is greater than, or a larger value, it is an indication that your member is much heavier than the other. Okay, so remember that the purpose of this economic section is to get really the economic section that is also uh, resistant to your loading. Okay, is capable in resisting your required loading. So in this case, This could be capable, but must have to be checked because your value is too close. Okay, although this is larger than this one. Remember that this S here is derived from live load only, right? It's only derived from your initial loading, that is live load. Your dead load still not considered here. And by you will check that one. So this could be one but must have to be checked. This could be one but must have to be checked also. And all of which should be checked. And the most priority from the three is the lightest. Okay. And the lightest obviously is this one because it has the lightest 82 kilogram per meter. Unlike here, we have 89 that is heavier, or 7 kilos per meter heavier than this one, as well as this one. So heavy, 101 compared to 82. Okay. So moving on, we're going to choose this section. So this is the section W610 by 82. Okay. And it is greater than your required 1666.67 times 10 raised to 3. So this is exceeding your S. Okay. So if we are going to check that one, of course we wanted to involve now the dead load. Because a while ago, we do not have yet a selected section. And by this time, once you have selected the section, you can now calculate or add your S due to dead load. Okay. Or the self-weight of your selected cross-section. So initially, we have already computed for this one S live load. Okay. And then we are now computing S of dead load. So S of dead load, just the same, this will computed according to your formula. Okay. So of course, what is the moment caused by your dead load or the self weight? So in the table, we can see that this is 82 kilogram per meter. And here it is loaded in your beam. Okay. So again, we have a ready-made formula for simply supported beam. Or if you want, you might do this shared moment diagram to come up with the moment diagram. But I suggest that you just remember this formula. That the maximum moment for a simply supported beam. When we say simply supported beam, we have a pin and a roller with a loading of distributed load. So on that, first we need to, of course, multiply this by 9.81. Or if you want, you can directly substitute that one. So this is 10 squared all over 8. And this is equal to 1025 kilogram meter. So here it is, the maximum moment. And it is located at the mid span of your beam. So on that, we need to multiply it by 9.81 in order to become Newton. Okay. So we have already Newton here. But your distance is in terms of meter. Remember that. Okay. So we need to express that in terms of millimeter to jibe with the unit of the megapascal here. So again, we can get the value 83.79, and then upon adding, you can see that the resisting S, or on the actual S, or the section modulus, is 1750.46 times 10 raised to 3. So this time, your S composes of two, live load and dead load. So we are going to compare this by your selected section. And your selected section is still greater than the actual section modulus of your chosen, or of your beam self. Okay, so therefore your chosen section is safe to carry the loading, okay, aside from the self weight. So there are cases that this exceeds the criteria S of your selected section. So what uh, what we will do on that case, we are going to select the next ranking from the table. Of course, the first ranking is, number one is to exceed your required, and then the lightest one. So the second lightest will be chosen if in case that this will exceed, okay, your selected section modulus. So we are okay on that. We have checked already the S, or the section modulus. Section modulus have a check mark on that criteria. And now let us check your actual bending moment. Okay, so why do we need to get the actual bending moment? So that we are going to divide that by your selected cross sections section modulus in order to come up with the actual bending stress. Okay, so initially we have already obtained the value of the maximum moment for the live load and the dead load as well. So all we need is to add that one. Okay, so this is 200 for the live load, 1025 multiplied by 9.81. This becomes Newton meter. Okay, we divide it by 1000 so that your Newton will become kilonewton. So finally, we have 210.06 kilonewton meter as the actual bending moment. So when we say actual bending moment, the required live load moment plus your selected the self weight, okay, or the self weight of your selected geometrical shape. Okay, so finally the actual stress will be equal to m over s, or moment is 210. Again, we multiply it by 1 million to make it in Newton millimeter, divided by your section modulus, which is 1870 times 1000. And we will yield to a value of 112.33 megapascal, which is less than your ceiling, or the limit flexural stress, equivalent to 120 megapascal. So your section is fast to carry the required loading. So next, another example. So we have a beam simply supported at the ends of a 25 feet span carries a uniformly distributed load of 1,000 pounds per feet over its entire length. Select the lightest S section that can be used if the allowable stress is 20 KSI. What is the actual maximum stress in the beam selected? So by the way, to recall, KSI is 1,000 pounds per square inch, or that is 1 kips per square inch, because 1 kip is actually 1,000 pounds. Okay, so we are going to have the same approach. First, we intend to get the live load. Okay, and the live load is 1,000 pounds per foot. This is the uniformly distributed load. To get the maximum moment, again, we have a simply supported. We can apply this WL squared L over 8. Okay, so this one, all over 20,000. So this 20,000 is your 20 KSI, or allowable bending stress. Okay, that is equal to 20,000 pounds per feet. So we are dealing with feet. By the way, square inch, sorry. 20,000 kips per square inch. So we are dealing with the inch unit. So we need to express your maximum moment in terms of inches. So remember, from this, we could arrive with this unit. Pounds per feet. Pound feet, sorry. Pound feet. So we need to convert feet in terms of inches. Okay, so 1 foot. 1 foot is 12 inches. That is why we have the factor here, 12 inches. So 20 KSI is further expressed in terms of pounds. So we have a consistent units in our equation. So we can get now this one, 46.875 cubic inches. And then from the table, we have a properties of I-beam section S shapes. We have actually selected a section with S greater than this one. And this, so far, this is the lightest section among the S shapes from the table. So S15 by 42.9. So it is greater than this. That is what we need. Then we have S59.6 greater than this, and then S resisting. So once you have chosen your section, you are now ready to add your section modulus for your self-weight or the dead load. So it was added here. So your live load was computed. Your dead load will be computed using the 42.9 pounds per feet. So this one. And this will be now your uniformly distributed loading all over a simply supported beam. And by that we can, again, we apply WL squared all over 8. So this is W, that is L squared, and that is 8. WL squared all over 8. So this is the maximum moment. Again, we need to convert it in terms of inch and then divide it by 20,000. So from this, we can get the modulus section, or the section modulus of its dead load, which will be added to 46.875 for the live load. We come up with 48.886. So we are going to compare this 48.886 to the S of your selected section, which is 59.6, and it is still greater than the actual 48.89. Therefore, your selected section have passed that criteria, and it is feasible to carry your loading. So we also need to check your moment. Okay, after checking S, we will now check your actual bending moment. So the actual bending moment, we'll just substitute your live load, uniformly distributed load is 1000. Okay, so your length is 25 feet. Okay, so 25 feet. And then we will come up with this 81,476.56. So this is pound foot. Moving on to the actual stress, we can see that this is again converted, divided by the S of your selected S, that is 59.6. And then from that, we can have this value, 16,404.68 psi. And 16.4 ksi is the equivalent. Comparing it to the allowable bending stress, we have 20 si. And still, that is less than your ceiling. So it means that it is feasible to carry the loading. So that's it for this problem. So another problem, a beam simply supported on a 36 feet span carries a uniformly distributed load of 2,000 pounds per foot over the middle 18 feet. So using an allowable stress of 20 ksi, determine the lightest suitable wide flange shaped beam, and then what is the actual maximum stress in the selected beam. So this time we have this beam from the conditions of the problem. You can see the 36 span carries a uniform distributed load of 2,000 pounds on the middle 18 feet only. So meaning from the middle, we measure 18 feet. And then the excess will be distributed on the left and right portion. So all in all, we have a length of 36. So this portion is unloaded. Okay. So of course, we cannot use the general formula for obtaining the maximum moment for a simply supported beam. So this is no longer simply supported beam. Simply supported, but your loading is not distributed all over the entire length. So therefore, you still need to go over with the shear and moment diagram. And of course, your criteria and the maximum moment is the area of the shear diagram. Okay, so from this, it is symmetrically loaded, so that 2,000 pounds will just be carried or shared by these two reactions here. And if we can see, we have here 2,000 times 18, and this is equal to 36,000. It will just be carried by both. So we just divide this by 2. So both has 18,000 reaction, the far end of the beam. So considering the shear diagram, we have this to push this shear diagram upwards by 18,000. No loading. We are going to deduct 36,000, 18,000 minus 36,000. We have negative 18,000. No loading. Then it will go back to 0 by this reaction. So from that, anyway, these shapes are equal. We have a positive and a negative area. So by symmetry, your moment diagram will just close because you have an equal positive area. And your maximum moment will surely occur at the point where the shear intersects the 0 line. So of course, we will have this positive area, and that is an area of a rectangle and a triangle. So in this particular section, so this is a straight line, and then when it comes to this, we'll add another units, and that is equivalent to the area of that triangle. So this is decreasing, so it must be concaving downwards. So we'll have an equal symmetrical effect to that. This must be. So what is important here is the value of this moment maximum. And it is actually denoted here on the live load moment. So 18 by 9 is this rectangle. Okay. Plus the triangle, 1/2 9. So half of 18 is 9 by 18,000. Okay. So we'll get 243,000 pound foot. And then again, you check S required. Okay. We compute for the S required. So 243 will be multiplied by 12 to make it in inches, because 20,000 is KSI, or kips per, or pounds per square inches. So we get an S required of 145.8 cubic inches. So we should look on a table wherein the section should have a section modulus greater than this one, 145.8. So moving on to the table, so we can see that this could qualify 146, but of course, obviously, if we are going to add your weight, it could be that it will right away excess or exceed this value, because your value is so close. So we're going to choose the lightest, and at the same time it is greater than this 145, and the lightest is this one, W24 by 68. So S is greater than 154, is greater than 145.8. So from that, we are going to check your S. Okay, adding now your section modulus caused by your dead load. So a while ago, we have already derived your 145.8 as your modulus of section modulus. This one, 145.8, caused by the live load. And then for the dead load, we have a distributed load force. The dead load is all over the entire length of the beam. So if that is the case, we can again use the formula for a simply supported beam. We have WL squared all over 8. So this is it. Substitute. So where did we get? We get 68 here from the section. So from the section, this should be 68. This one, 68 pounds per foot. So that's the meaning. 68 pounds per foot. Of course, that 68 will be your W. We substitute the overall length and divide it by 8. So we need to multiply it by 12 to make it in inches, so as to be consistent with your allowable 20,000 pounds per inch. So from that we can derive 6.61 cubic inch, which will be added to section modulus of the live load. So we'll come up with 152.41 cubic inches. So from that, we're going to compare this by your selected geometrical shapes section modulus, which is 154. So 154 here is exceeding the actual or the resisting S calculated. So therefore, that is noted as okay. And then after that, we are going to check your actual bending moment as usual. We substitute the values. So a while ago, this was already derived. Okay, this one. 243,000 pounds foot. And the dead load is that one, 1868 times 36 squared. So the actual bending stress or bending moment is 254,016 pound foot. So that we get the actual flexural stress equivalent to 19,793.45, or that is 19.79 KSI, which is less than 20 KSI, so it's still okay. So that's it for this problem. And then for the next problem, let us consider a simply supported beam 24 feet long carries a uniformly distributed load of 2,000 pounds per foot over its entire length and a concentrated load of 12 kips at 8 feet from the left end. So if the allowable stress is 18 KSI, select the lightest suitable W shape. And what is the actual maximum stress in the selected beam? Okay, so we consider the condition of the problem. Aside from the 2,000 pounds per foot distributed over its entire length, it has a concentrated load. 12 kips measured 8 feet from the left end. So 8 feet from the left end, we have this 12,000 plus the 2,000 pound per foot loading distributed all over this 24 feet beam. So the first thing to do is to establish your shear diagram. Anyway, shear diagram will just give you the shape that will be your basis in the ordinates of the maximum bending force. So of course there will be no, your beam is no longer symmetrically loaded. You need to perform summation moments R2 and summation moments along R1. So by doing that, we will have R1 32,000 and R2 is 20,000. So we can check that by adding both. So by adding both, we have 60,000 upwards. Okay, and your downward force is 2,000. It should be 2,000 times 24. So in fact, this is 48,000 plus 12,000. All in all, downward force will be equal to 60,000. Just the same, your upward is 60,000 also. So plotting the shear diagram, we start with an upward 32,000 here and then deduct the rectangle covered by this 8 feet length. So that is 8 by 2,000, that is 16,000. So therefore, 32,000 minus 16,000, we will yield to 16,000. Still, that is a positive one. We go 12,000 units downwards. So still, we have a positive 4,000. And then we deduct the remaining rectangle here. That is a downward, so that is minus 2,000. And what is this dimension? So if this is 8, this should be 16. So therefore, 4,000, this is 2,000 times 16, 32,000. So therefore, 4,000 minus 32,000, that is negative 28,000. So your maximum is no longer at the midpoint. So we need to locate your maximum. So in this case, x is delegated as the dimension of this triangle, and the remaining dimension for the smaller triangle here is 16 minus x. Okay, we have a ratio and proportion of this triangle smaller to that of the larger triangle. So we can say that x, the base of the larger one, is to the height of the larger one, 28,000, will be equal to the base of the smaller one to the height of the smaller one. So by cross multiplication and manipulation, x will be equal to 14 feet. So this is already placed here in the figure. So for the live load, of course, this is the shear diagram. Remember that this positive area will just be equal to this negative area. You might want to consider this left portion for the value of the moment, but it is much convenient if we use this single shape that is a triangular section. So we have 1/2 14, okay, so the base is 14 by 20,000. So we have 196,000 pound per foot. So this is the largest or the maximum moment located at this distance. And this distance, since this is 14 feet, this is 2 feet. Adding it to your 8 feet, therefore, from this up to the location of the highest moment, this is 10. Okay, so that is 10. So anyway, we will be needing this distance by and by, this 10. And then from that, we compute the S required. Again, this came from this formula. Okay, so we utilize the allowable. So we substitute your maximum, this one, times 12. So this is to express this into inches. Okay, so we will have an S required of 130. And then from that, we select a shape with S greater than 130. So choosing the second to the, or the lightest, say the lightest is 62, but has is slight, only slight difference to the required S. So we wanted to check this one first. So the first thing to check is the S. So from that S of 130, we need to determine the moment caused by the dead load as well as the section modulus for the dead load. And your dead load this time, or the maximum moment, is no longer at the center. So we need to refer it to the location of your maximum moment. Okay. So we will have this portion. And a while ago, I have marked this location as 10 feet, so that the remaining here is 14 feet. So from that, we will be utilizing this area here, considering this height. So we'll be having a trapezoidal area here. Of course, we need to get this height y. So y could be computed by similar triangles of this triangular section. So we can say that y is 2 feet. Okay, because this is 10, so this is the half, the remaining is 12 minus 10, that is 2 feet. So y is to 2 for the smaller triangle is equal to larger triangle, 744 all over 12 feet, or the half of 24. So by cross multiplication and manipulation, we have y is equal to 124 pounds. So from that, we can now compute that the maximum moment dead load by this trapezoidal area. And that trapezoidal area could be solved by this formula, 1/2 B1 plus B2 times height. So the first base is 744. Okay, so here it is. This is 744, and that is 124. So 744 plus 124, so it's 1 times the height. So actually this is 10. Okay, so we come up with 4,340 pound-foot. And then again, this will be multiplied by 12 to make it in inches, divided by the allowable 18,000. So we will be having a 2.89 cubic inch, which will be added to your section modulus caused by the live load. Okay, so we have 133.56. So this time it has already exceeded the S resisting, or the S required, which is supposedly 130.67. So the value 133 is already greater than your resisting S is equivalent to 131 or S squared. So this is the time we are going to select the second lightest. So this time we are going to consider wide flange 21 by 68. So 68 pounds per foot. So it has a section modulus equivalent to 140 cubic inch, which is far greater than 130.67. And then again, first thing to check is the S. So S is already determined 130.67, and then we get Y here. Okay, so a while ago we are dealing with the dead load of that member. So this time this is the dead load of the new selected member, double 21 by 68. So we ration proportion, compute for the moment dead load and the S dead load equivalent to 3.17 cubic inches. So remember that for 760 will be added to the moment live load, and this S dead load 3.17 will be added to your section modulus for live load. So the moment live load is already computed a while ago. S for the dead load is our live load is 130 also. And then we consider a critical section. Of course, we will be computing the Y earlier. We compute that Y earlier. Okay. So where's that Y earlier? So here it is. So you'll just be dealing with a trapezoid equivalent to the reaction plus the value of weight Y times the height. That is why we are calculating Y here. So that we can proportion it then. So we can say that Y is to 2 is equal to, so S resisting is checked already, wherein the S resisting is exceeding your actual S live load and S dead load, okay, which is 133.84. So we use W21 by 68. The actual bending moment is computed as well. We have this one, and then your actual stress will be less than your allowable 18 KSI. So this time, the second selection will be most suitable to this problem. So this is what I'm telling a while ago, that we need to consider Y here, okay, for your M dead load and S dead load. So that is for this video. So I hope you will be ready for an evaluation next meeting. So thank you for listening and have a good day.